Okay, in this question we're told that we have a cube of aluminium which has equal sides 8 centimeters in length, and we're also given the density of aluminium. And we're told that this is placed in water, and we need to work out whether this will float or sink. Then for the second part of the question, we're told that the same mass of material, that's made up that 8 centimeter block, is formed into a hollow box, but with sides 20 centimeters. And will this float or sink? And if either of these float, then we need to calculate the depth to the bottom of the box from the height of the liquid. Okay, so the way we go about this question is we know that it will float if the weight of the object, so the mass times gravity, is less than or equal to the buoyancy force, which is obviously trying to push it up. So we just need to work out each of those values and compare them. So for the 8 centimeter cube, its weight is its mass, which is density times volume times gravity. So we use the density of the aluminium that we're given from the question times by the volume. Remember, we need to get this into meters cubed, and we work out that would exert a weight of or a force of around 43 newtons. Now the maximum buoyancy force that we can have is when it is just fully submerged. Okay, so in other words, when the whole volume is just under the surface of the water. And the buoyancy force that you'd get then, again, buoyancy force is given by this equation, so rho GV, but here the rho isn't the density of the object, it's the density of the fluid. And the density of the fluid it's going into is water, so we have 1,000 times gravity times the volume of the object. And if we put that into our calculators, we find that we have a buoyancy force of 5 newtons. So therefore, since the weight, the force due to gravity, is higher than the buoyancy force, it will sink because it would be pulled down to the bottom. For the second part of the question, we're told we have the same mass, but it's made into a bigger shape. Okay, a cube that has 20 centimeter sides. We don't need to work out the weight again because we're told it's the same mass, so it's going to have the same weight. But we do need to recalculate for the buoyancy force. Okay, and again, if that volume is completely submerged. So we use this one again, remembering that the density in here is the density of the fluid, which is water, not the density of the thing that we're interested in. If we all that out, we get a buoyancy force of around 79 newtons. So in this instance, the buoyancy force is greater than the force, gravitational force trying to pull it down. So this will float. Okay, so we know that. So now we need to do the third part of the question and work out how much it floats by, where is the bottom of the box. So we know it will float, but what we're trying to find now is Z, where the bottom of the box is in relation to the level of the liquid. And we know that for this to be in equilibrium, so if it's not bobbing up and down, then the buoyancy force must be equal to the force due to gravity, the weight of it. Okay, so that's what we're saying here. When it's in equilibrium, the weight is equal to the buoyancy force, which is equal to rho GV. So we can rearrange this in terms of volume. Okay, so we've got the weight divided by density times gravity, remembering it's density of water, and we end up with a volume of 4.35 times 10 to the minus 3 meters cubed. Okay, so that is the volume, the equivalent volume that you would need to match the weight. So that tells us the volume that is below the surface of the water. And if we know what the volume of the surface below the water, we know what the area is of one of the faces, because we're told it's 20 centimeter cube. So if we know what the area of one of these surfaces is, then the equivalent volume will be that area times by Z. Okay, so we can use that to find out Z. So the volume is the area of one of the surfaces times by Z, which is equal to this volume that we need to make it float. So we have one equation here with one unknown, z. We can rearrange that equation, and if we do, we end up with an answer of 0.109 meters or 10.9 centimeters.